In this video, we're going to start the last main section in this course, and that is talking about hypothesis testing, as all the different variations we're going to see in this class and the different ways to get the answer, but they're all going to be in the same genre of hypothesis testing. And this is an incredibly important part of statistics because here is where we're doing the inferential part, where we are trying to make a decision about what's going on, and this is the framework that we're going to use to help us make that decision. So let's say a city is trying to decide if they want to change an intersection from a stop sign to a stop light, or maybe they're going to take an intersection and that has no stop sign or stop light, and they're going to add a stop sign in or something like that. Well, that costs money. And so they need to decide, okay, well, how many accidents are we going to help avoid? How much traffic are we going to help alleviate? Is it going to be worth spending this money to upgrade that intersection? Well, the thing is there's randomness, right? Traffic is not the same from exact day to exact day. There's randomness going on. Accidents don't happen exactly the same time every day. They're random as well. And so we can never be sure exactly how much money we're going to save by making this decision, but we want to then do some sort of calculation, some sort of estimate, and try to say, is this going to be a good idea? Or we're trying to make a decision. There's an example we're going to have in one of the later videos where we are trying to get a certain law passed. This law is going to be favorable to our company. We take a sample, we get data from that sample, and we say, okay, well, based on this sample, we don't think the law is going to pass, so we then decide we want to put some advertisement dollars into that, try to convince people that this law is actually a good thing. And then we like to see, is that going to help us change the perception among the public? So there's lots of types of questions where you want to try to figure something out, you want to try to make a decision on what to do, and we are never going to be able to get perfect information for pretty much anything in this world. So we have to make this decision based on limited information. And that limited information was hopefully gathered in some sort of random fashion. And then we can use the methods of statistics to answer that question. So again, in this video, we're going to go over the basic framework that is going to be used. And then in future videos, we're going to have, here's the hypothesis testing in this special way. Here's how we get the answer. And then here's hypothesis testing in this other way, and so on for every other video. But this is the framework. So every hypothesis testing is going to have a null hypothesis and an alternative hypothesis. There's always going to be two hypotheses. The null hypothesis, which we're going to call that H0, this is going to be whatever assumption you begin the problem with, slash whatever would represent the normal scenario, slash whatever means no change is happening. So the idea is the null hypothesis, it's always the boring one. It always means that it's the default assumption. It's what would be like in the normal scenario. It's when nothing's changing. Let's say you want to take a test to see whether you have a disease. Whatever disease you want to talk about, whether it's COVID or some other disease here, there's going to be like the normal body functions, and then they're going to measure something about you, something in your blood or something, whatever other bodily fluids they take. They're going to measure that, and they're going to see whether it is in the normal body functions range or is it in the unusual body functions range. That means maybe you have the disease, right? For example, to take your temperature. We have a normal range for temperature for people that are well, and then we have maybe elevated temperature, higher amount, that means you have a fever. But what we're trying to see is it just a little bit of a fever? Is it enough that maybe they're sick or not? But regardless, you're always taking the boring option, the thing where everything's normal. That's your null hypothesis. So in the example where you're trying to determine if someone's sick or not, the null hypothesis is that they are fine, that they are normal in that case, that they're not sick. The alternative hypothesis, that's going to be your H1. This is always going to be whatever you want to prove with the data. So if you're trying to show someone's sick, has COVID or whatever with the data, that's going to be the alternative hypothesis. And it's always what you are trying to prove. That's what goes in H1. You are never going to be trying to prove the null hypothesis H0. In fact, it's impossible for us in this framework to prove the null hypothesis. So when we get to our conclusions here, the conclusion might be that H1 has essentially been proven statistically, or the conclusion might be that H1 has not been proven statistically. The conclusion will never be that H0 was proven statistically. That's never going to happen. You're either going to prove H1 or you're not going to prove H1. Those are the two possible scenarios. Now for us, at least for our basic tests here, our H0 is always going to be something equals a number. And that number is going to be specific, right? So maybe it's mu is going to be equal to a number if we're trying to test about the mean. Or let's say we're trying to test about proportion, P is going to be equal to some number. And maybe I'll just use specific numbers here so it's clear. Say mu is equal to 17. Or I believe P is equal to 30%. Or I believe the standard deviation is 5. So these are all going to be the default assumption. It's equal to some value. Every single one we're doing right now is going to look like that. However, there are things you can have different in your alternative hypotheses, your H1s here. So a left tail test, that's when you're trying to prove that the value is actually smaller than what you thought it was. So originally people thought it was 17. We're now trying to prove it's smaller than that, and this is going to be called a left tail test, because if you think about drawing the graph here, if 17 is the middle, we're trying to prove that it's something less than 17. That's going to be on the left side, it's a left tail test. If I want to actually try to show something is bigger in this case than say 30%, that is going to be a right-tailed test. And if we're in the scenario where we're just trying to prove that it's something different than it was before, we don't know if it's more or less, all we're trying to prove is something has changed, this is called a two-tailed test. And so you need to be able to look at hypotheses, identify which one it is. In fact, when I go through and show you how to use your calculator for these problems, that's going to be an option. It's going to say, is this test a left-tailed test? Is this test a right-tailed test? Or is this test a two-tailed test? You have to select the correct option, otherwise you're going to get the wrong answer. So just keep that in mind. These are how we identify which test is which. Now, at the end of the day, there are going to be two possible conclusions. As I said already, option A is you have proven the H1. You prove that H1 is actually correct. Or B, you have not proven H1. Now again, you are never going to say that you have proven H0. That is not a possible conclusion in any of these hypothesis tests. You either statistically prove H1 is true, or you just haven't proven it. Well, here's the thing. So these are the two possible conclusions. Each one of them, you could be right or you could be wrong. And that means that there's going to be two possible errors, and we're going to call them type 1 errors and type 2 errors. And to be honest, I quite often mix up which is which, so you always want to double check these and make sure you are doing the correct thing here. So for a type 1 error, what does this mean? This is when H0 is actually correct, but you claim to have proven H1. So you get your data, you decide that H1 is actually the correct hypothesis. You're saying you've proven it, but you're actually wrong. It turned out that in the real world, H0 was actually true, so that would be the wrong mistakes here. This would be a type 1 error. And the way I think really makes more sense for people is thinking about, let's say you're testing for a disease here. So if you're testing for a disease and your H0 is actually correct, that means you are not sick, but the test is claimed to have proved that you are sick. So this is what we call a false positive. This is saying that you have COVID, but you actually don't have COVID. That's a type 1 error here. On the other hand, the type 2 is going to be the exact reverse of that. And this is going to be when H0 is actually false, but you claim you can't prove H1. And so this would be the false negative. This would be your test came back and said you were normal, you didn't get anything different, but in fact you are sick, you are not normal in that case. And so I briefly mentioned this in another video, but the idea is whenever you're designing these tests, and we're going to see that as we go through this, the type 1 error and type 2 error for a test are always going to be related. If you try to modify your test to make the type 1 error happen less often, you are then going to make the type 2 error happen more often, and vice versa. So when you are designing a real-world test, you can pick one of these to make really, really small, but that's not going to make the other one really, really small. In fact, it's going to make it larger than it would need to be. So you can't make both of these really, really small at the same time. That means that if we're going to have a COVID test that is pretty much always right when you have COVID, that means it's going to say that you're positive when you are actually COVID positive. So there's no false negatives or very few false negatives. That means there are going to be more false positives. And we have decided that when making the test that that's the better scenario. Because if you actually have COVID, but you think you don't because the test gave you a false negative, that's a really bad scenario because you're going to go out interacting with people and you're going to be spreading COVID when you thought you were perfectly safe. On the other hand, the worst case scenario if you get a false positive is you end up quarantining when you didn't really need to, but that's still safer than going out and interrupting. So we decided as a society that the type 2 error in that situation is worse, so we designed the COVID test to minimize type 2 error, and that means there are going to be more false positives. And that means some of the tests, they may say they don't want to give you the test unless you're showing symptoms, and that's because the test has a decently high false positive rate. So they don't want to give you the test if you're not showing symptoms because it might say you're positive when you're really not. And we'd rather you not have to think that. So we wait until you actually have symptoms. Then we give you the test. And then, we don't have to worry about the false positive as much in that case. So we don't want you just testing every day for no reason. We want you to have some sort of symptoms or some sort of exposure before we decide to give you that test. Now, for every hypothesis test, there is going to be something called a level of significance. We are going to call this alpha. And it will be given to you in every problem. And this is the probability of a type 1 error. So this is going to be built into the hypothesis test. When you're doing your calculator, it's going to ask you what alpha is. You plug it in there. It'll do your calculations. Sorry, actually, it doesn't plug into the calculator unless you do it a certain way. The way we're doing it, we're going to avoid plugging the alpha in the calculator, but you're going to use alpha to determine your final answer. Regardless, it's the chance of getting a type 1 error. Now, there is something else that's kind of like the chance of a type 2 error called the power of a test, beta. We don't get into that in this class, thankfully, because it's quite a bit more complicated. But the idea is, again, you can't make alpha and beta both really low. You can only make one or the other really low. And so alpha is going to be given to you in the problem, and then you're going to base things off of that. alpha is the level of significance. It's the probability of type 1 error. So it's the chance that if the null hypothesis was actually correct, it's the chance that you would still claim to have proven the alternative hypothesis. And we'll see that in a specific example later on. So these are the terminology that we are going to use when going through all our hypothesis testing. Future videos are going to be just looking at specific versions of hypothesis testing and how we do the calculations and how we make our conclusions.